Hello everyone, it's Benny, and welcome back to Occlusion Culling. Last time, we talked about portal-based occlusion culling, which is a great technique, but it had a few notable shortcomings to it. So today, we're going to talk about a very closely related technique that can overcome a few of those issues, and that is the potentially visible set. This is another technique that's been around pretty much forever, ever since the earliest 3D games, and it's still pretty common today. In fact, as of this recording, if you were to download Unity 3D and open it up and tell Unity 3D, hey, do occlusion culling for me, this is a technique that Unity 3D uses. So, it's still used. It's still a great way to do it, under certain conditions. And yeah, let's go ahead and let's get into it. Let's talk about how this potentially visible set nonsense works. So, like nearly every occlusion culling algorithm, the first thing you're going to want to do is to divide your scene into different parts that I'm going to call nodes. So this is node 1, this is node 2, 3, 4, 5, etc. And these barriers, these imaginary barriers connecting the nodes, are called portals. Now, how exactly you take a scene and come up with this representation, it's a little bit scene dependent, and it's outside the scope of this video. I'm going to have a separate video talking about the different ways to do this, and what works best with different scenes. For now, let's just say this is our scene, and somehow or another, this is how our scene got divided into nodes and portals. So great. Once we have that, now what? How do we make a potentially visible set out of this and do some occlusion culling? The key concept, for every node, we have a list of what nodes it's at least possible to see from somewhere within that node. So for example, in node 7, what can we see potentially from somewhere in node 7? Well, just intuitively looking at the scene, you can see, okay, we can see node 6, and 1, and 2 from somewhere in node 7, and we can probably see node 3 from somewhere in there as well. So that would be our potentially visible set, nodes 6, 1, 2, and 3. And we just build a list like that for every node. That's it. That's the whole concept of a potentially visible set. There's nothing else to it. And so once we have that potentially visible set, these are the nodes it's possible to see. If the player's in node 7, we'll look up at this potentially visible set, say, okay, for node 7, these are the nodes it's possible to see, that's what we render. Simple as that. This is a really simple algorithm in concept. Now, there is one catch to this, and don't worry, it's only one catch, and you might have seen it earlier. Because earlier I said, from node 7, we can just sort of intuitively look at the scene and say, nodes 6, 1, 2, and probably 3 are visible from somewhere in node 7. We can do that with our intuition. How do we turn that intuition into a computer algorithm so the computer can decide these are the nodes that are probably visible from somewhere in node 7? That's a little bit tricky, but it's actually not too terrible once you work through it. So let's talk about that. So, there are two parts to this algorithm, and the first part is pretty straightforward. Now, let's use node 7 as our example, just because that's what I've been doing the whole time. Let's say we're in node 7. We already know, before we do anything, that node 7 has a portal, because the portal was created when we sliced up the level. And we know that node 6 is behind the portal. So actually, we can immediately add node 6 to the potentially visible set before we even do anything. Why? Well, if this portal wasn't visible from somewhere in node 7, the portal wouldn't exist to begin with. The portal's kind of a giveaway that node 6 is visible from somewhere in node 7. So, yeah. And we can just go ahead and do that for every node. For every node, we look at all the portals in the node. And we add the node behind the portal, because obviously the portal is visible from somewhere in the node, and therefore the node behind it is visible from somewhere in the node. So 1 has nodes 6 and 2, because that's its two portals. 2 has nodes 1 and 3 because those are behind its 2 portals, and so forth and so on. These are the quick, easy pickings. These are obviously visible from somewhere in the nodes. That said, this potentially visible set is not complete yet, because, again, if I'm in node 7, if I look through the portal, I can see node 1 from somewhere in node 7. How do I know that? That's where the second part of the algorithm comes in. But this first part is all there is to it. Just look at the portals in each node and immediately add whatever nodes are behind those portals. There you go. So, how do we know that node 1 is visible from at least somewhere in node 7? Intuitively, it's pretty obvious. And what your intuition is probably doing is a line of sight test. Because there's a line of sight from somewhere in node 1 to somewhere in node 7, well, therefore, there's a position in node 7 where you can see node 1. If I'm standing right here, I can look down this line of sight and see somewhere inside node 1. So therefore, node 1 is potentially visible from somewhere in node 7. So that's great, but how do we generalize that into an algorithm? The algorithm can't magically know, hey, this is the correct line of sight. Well, let's start by looking at the extremes. What's the most extreme possible line of sight where we can still see somewhere in node 7 from node 1? Let's try right here. If I try right here and I draw a line of sight, you notice, hey look, I can still draw a valid line of sight from somewhere in here to somewhere in node 7. If I try going more extreme, you notice, oh hey, here it's no longer possible to see somewhere in node 7 from node 1 because this corner right here is blocking the line of sight. So obviously somewhere in this region there's a perfect line of sight where you can just barely see node 7 from somewhere in node 1. And you notice the just barely point seems to correspond to this corner. This is the most extreme corner of node 7. So we can kind of do this in reverse. If I start here and just start moving further and further over in node 1, where do I hit the corner? Right about here. So this is my most extreme possible line of sight. Somewhere along here, I can just barely see this corner of node 7, which is just barely not blocked by this corner in node 1. So cool, we have our most extreme line of sight. And you might notice something. The most extreme line of sight happens to correspond to the line between the two corners of the portal. In fact, if we try this trick again, like this, just connecting the two corners of the portal, this is also the most extreme line of sight in the other direction. From here, I can't see node 7 without this corner blocking me. But if I go on the other side, what do you know? I can start just barely see into node 7 without the corner blocking me. So that's how you generate the most extreme line of sight. You connect the two corners of the portal, and boom, most extreme lines of sight. In fact, I already drew this out nice and neatly right here. So there you go. So that's our first insight. We now have the most extreme line of sight. Our second key insight, if I go ahead and erase this really quick. The second key insight is that anywhere in here I have a valid line of sight to node 7. Anywhere between these two extremes is valid. And yeah, anywhere in here I can see somewhere in node 7. Anywhere outside of here I can't see somewhere in node 7. So this forms almost like a cone of visibility. Or really, you might even say a frustum of visibility. Yeah. So this is the trick. We take our two most extreme lines of sight and we use them to create a frustum. And this frustum will encapsulate every possible valid location that we can see, well, in node 1 from somewhere in node 7. So this is just a cool trick. You generate a view frustum that encapsulates everywhere we can see in node 1 from at least somewhere in node 7. It's a cool little trick to generate something that does that. And this is the trick to how we're going to figure out what we can and cannot see from somewhere in node 7. So, now that we have this view frustum, a few things become pretty obvious. Firstly, this portal, the portal to node 1, is within the view frustum. So clearly, we can see node 1 from somewhere in node 7, therefore it's part of the potentially visible set for node 7. And this portal, which is connected to node 1, this portal is also within the range of things we can see from somewhere in node 7. So we can add node 2 to the potentially visible set, because we can see node 2 from somewhere in node 7. Here's the thing though, this portal in node 2, that's going to restrict our visibility. This is going to restrict how much we can actually see from somewhere in node 7. How do we compute our new restricted view frustum? Because we can't use the same trick we used in portal occlusion culling, because this is only a virtual view frustum. This is not where our camera actually is. We need a different way of doing this. Well, let's take a step back for a moment. Let's pretend we're actually in node 6 somewhere. What can we see from somewhere in node 6 through this particular portal? Well, we can use the same trick we just used, because there's only 2 portals here, like before. So we'll connect the most extreme corners of the portals. This gets us a new view frustum. And there you go. This view frustum is everything we can see from somewhere in node 6 through this particular portal, right? Now, that's great, but we still have our frustum from node 7. This is everything we can see from node 7 through this particular portal. But note, that includes everything we can actually see of node 6. Do you see where I'm going with this? So this has what we can see from somewhere in node 6. This has what we can see from node 7, including what we can actually see of node 6. So we're going to clip these 2 frustums together to get a new view frustum, and that'll be what we can actually see from somewhere in node 7 through this particular portal. Now in this case, clipping the view frustums together just gets us this view frustum, so no change, but you'll see a better example in just a moment. So this is what we can actually see from somewhere in node 7 through this particular portal. Now, it becomes pretty clear, this portal, the portal to node 3, is within this view frustum, so we can see node 3 from somewhere in node 7. So that can be added to the potentially visible set. But to keep going, we're going to want to clip our view frustum even further. Strictly speaking, in this case we don't have to, because the portal is already outside, but just to show you an example of where the frustum actually gets clipped, I'm going to do it anyways. So, once again, we're going to use the same sort of trick. What can we see of node 3 from somewhere in node 1? Well, we'll generate the most extreme lines of sight by connecting the edges of the portal. This makes a virtual view frustum here. And this frustum, the yellow frustum, that encapsulates everything we can see in node 3 from somewhere in node 1. Now, our original frustum has everything we can actually see of node 1 from somewhere in node 7. So if we clip these 2 frustums together, we get this frustum. And this is everything we can actually see of node 3 from somewhere in node 7. And as you can see, yeah, it doesn't change anything. We still can't see the portal from somewhere in here, so we're done. This is everything. But I just wanted to show you what it looks like when the portal actually the frustum actually gets clipped when doing that. So there you go. Now we have the complete potentially visible set of node 7. That's how you do it algorithmically. And this is everything there is to building a potentially visible set. If you understand that, that's it. That's how you build a potentially visible set. Those are the 2 parts to building it. So, lastly, we have to do that same line of sight frustum clipping thing for all the remaining nodes to get the final potentially visible set for every single node. So I'm going to go through this rather quickly. If we do that for node 6, we find out nodes 2 and 3 are still visible, so that's the final potentially visible set for node 6. For node 1, 7 and 3 are visible. Node 4 is not. For node 2, 6 and 7 are clearly visible, and the rest is a little bit interesting, so I'm just going to go through the same trick a little quick just to show you. Connect the two extreme lines of sight. This is what's visible through this portal from somewhere in node 2. There's the frustum. Portal to a node 4 is visible, so there you can add that. Then you want to clip against this portal, so generate the extreme lines of sight from this portal, from somewhere in node 3 to somewhere in node 5. You clip them together to get what you can actually see from somewhere in node 2 and somewhere in node 5. That gets you this. And there you go. Strictly speaking, you didn't have to do that, but I just wanted to show you the clipping thing in action to help you just see how it works. So it's obvious, node 5 is visible, and there you go. So node 3, everything's visible again. Node 5, turns out 4, 3, and 2 are visible, and node 4, turns out node 2 is visible, but not 1. There you go. This is the complete, potentially visible set for every single node in the level. So, this is the final potentially visible set for all our nodes. That's it. There's no more tricks to it. There's no more computation or extraneous edge cases. This is it. This is everything. But, optionally, there's one more thing you can do to optimize your potentially visible set. If you want to. This is optional. If two nodes have the exact same potentially visible set, including itself, so for example, nodes 7 and 6 meet this criterion, because if you include the node itself, these are exactly the same potentially visible sets, just in a different order. So if that's the case, you can actually optionally merge the two nodes, because it won't make a difference in your final runtime, because the potentially visible set's exactly the same. Going from node 7 to node 6 won't change your set of things the game says is visible. So if you merge all the nodes that have the same potentially visible set, this is what your new scene looks like. And note, this is exactly equivalent to what we had before in terms of runtime. Exactly the same things will be visible at exactly the same time. It's just, this is a lot smaller and there are a lot fewer nodes. So this is just a nice trick you can do, optionally, if you want to make a smaller potentially visible set, or have fewer nodes overall in your level. So yeah, that's everything there is to potentially visible set occlusion culling. So how does this hold up? What does it do well? What does it do not so well? And how does it compare to the algorithm in the last video, portal occlusion culling? Well, the biggest advantage to this approach is it's very fast. You can, hey, at runtime, you just say camera is here in node 2. The potentially visible set for node 2 is nodes 2, 1, 3. Draw those. Done. It's hard to get much faster than that. It's also pretty good at accuracy. Now you notice in this example, it's not perfect. It says node 3 is visible even though it's not. But what you can do is you can sort of narrow it down at runtime. You say, there's a potentially visible set for node 2, and for each node, I'm going to test to see if the portal to that node is actually in the view frustum before I draw it. So node 3, the portal to node 3 is outside the frustum. We wouldn't draw it even though it is in the potentially visible set. So you can sort of narrow this down a bit at runtime to get better accuracy. You can actually combine this and portal occlusion culling together to get pretty much the best of both worlds. So it's a really useful technique like that. Unlike portal occlusion culling, this is not limited by the number of portals in your scene. You can have as many portals in your view frustum as you want, and this doesn't care because it's not using portals at runtime. All it's doing at runtime is looking up, this is what's potentially visible, do that. So that's really cool. And in fact, because of that, this can work well in scenes that are traditionally not suited to portals because it doesn't care how many portals you have. You can put as many portals as you want in your scene in order to get a good division for this algorithm to work. And it doesn't care because it's not using the portals at runtime. Unless you're doing some occlusion culling like that, but even then, that's usually okay. So this has a lot going for it. This is a great way to do occlusion culling. But there's always a but, isn't there? This still only works on static geometry. You're not going to get dynamic occlusion culling working like this well, maybe you could do some really special tricks to get it to work, but in general, this is for static scenes only. Also, this requires even more special pre-processing than portal occlusion culling, because not only do you need the portals, but you need to do that chained visibility calculation to find out what is or isn't visible from every single node. So if you're already spending a lot of time pre-processing, you might want to consider that when you're choosing this as your algorithm. And, like I said, it's still less accurate than portal occlusion culling. It's pretty close. It's not less accurate by a lot, but it's still a little bit less accurate. So that's another thing to consider. So, overall, good algorithm, but still has some notable limitations. Especially the limitation about static geometry. I mean, surely there has to be some algorithm that would still do occlusion culling really well, even if the geometry isn't static. Surely there must be a way to do that. How could you do something like that? Find out next time! I hope you enjoyed, I hope you learned, and I'll see you in the next video.